So hey guys and girls, welcome to the episode, second episode of Gangster Math. As you can see, I'm wearing a white beanie, white hat. That means I've been caught by the police. So technically, I'm not able to say some of the things that I wanted to say, the type of stuff that I said in the last video. But more importantly, the reason is because we're going to cover the basics of derivatives today, and that's tough. So I have to be accurate, okay? I don't want to be, making a lot of garbage explanations that are wrong. I don't like to be wrong. I like to be interesting. There's a difference. Anyways, first of all, we're talking about calculus. So the first question we gotta ask is, what is calculus? Now let's start from single variable. Single variable calculus is basically what you can do on a plane, not on a flying plane, on a flat surface. Okay, you take any flat surface, the width of the surface is 0. It's just basically this piece of paper. And yes, I am certain that there's stuff you can do to the paper itself to morph the paper and create a plane that is curved. But for the sake of single variable calculus that we're dealing with in high school and first year, it's on a plane that is flat and also, not curved. I'm sorry. On a plane that is flat and not curved. Okay. Yeah. On a plane that is okay. So, um, what this means is we can think about what we can do on a flat plane, right? We can talk about painting, right? Of course, color is not something that is done in mathematics. I guess you could input a number for the color and make it mathematical. Mathematics, although a lot of textbooks use color, the color of the shapes, etc., is just black and white, red and white, yellow and white. There is no specific information in terms of calculus thinking that does anything. It's not. A lot of times, professors are going to denote this color, this one yellow or whatever, but in reality, it's not like, oh, I'm going to have a function and I'm going to have some type of yellow function versus a red function. The yellow function and red function are the exact same, and then you put them on two planes and do the exact same function. But one of them you drew it with the red. So let me just give you an example. Let's say we have x squared. I draw x squared on one set of axes with the red marker. I draw x squared with another set of axes on a set of axes with a blue marker. Is there any difference? No. Or you can say, oh, this one is red and that one is blue, but they're both x squared. The only information the function is giving you is the shape of the curve. So whether it's blue or red, they're identical. There's no difference. Now we got that out of the way. Also, it's like, what can I do else? I can find the area, I can find, let's say I draw some random function. Function is basically something that draws on a calculus. On a calculus, on a plane, yeah. So basically, a function is just something that draws on a plane, right? Sometimes you can think about functions that take more than one variable and then output something. The important thing is that there is one output. So everything, whatever you do with the multivariable, whatever, there's always going to be just one output. Right? So we're talking about obviously it's more complicated with multiple variables, but with one variable, it's a line, right? And with multiple variables, as you can tell, I'm a 70 student, but I haven't studied calculus multivariable for a while. But if I just remember, let me see. Yeah, it's the if it's multiple variable, it becomes a surface. That's the output. The output is a surface, like you know, a, a, a layer of dough, right? You take a dough, you know, dough like flour to like make tortillas and stuff. It's like a sheet, right? That's what multiple variable is, because if you have three variables, um, functions are two variables, but there's three variables. There's x, y, z, right? So it's x, y. For each different x and y, there's gonna be a z above it, and so at every point, um, every single point on the surface within the range. And what's the other word? I forgot the other word for it. Something called um, domain and range. Yeah, within the domain and range, um, every single thing on the flat surface is gonna. That's that, and so that's the calculus. Um, you can find things like we can talk about before we talk about the area. Area is very interesting. How can we do that? Let's say, well, if you have now, here's the fundamental theory of mathematics that I am sort of on. This is my PhD here, guys. Shall I do a PhD? I challenge you to prove that any drawing you can draw on a piece of paper, you can draw it with piecewise functions. Is that possible? That's the question. So that's the interesting question. Again, my classes are so interesting already. Just think about it though. Is it possible that, let's say I draw some random squiggly shit? That's not a function. Yeah, okay. But, okay, that's not a, how about any shape where it doesn't go back on itself, it passes the test, what's it called? The vertical line test, which means if I put a vertical line through any spot on the function, it will only hit one point. So I can, okay, so that's the question. Can I put any point on the function? Can I make a, you know, can I make a, can I make a function that says and draws exactly that? Right. That's an interesting question. I think that's more interesting than what's that guy called? Anyway, some famous mathematician came up with a question that like x4 or the or the quintic. There is no there is no there is no formula for the quintic and above or sextic and above equation something. So yeah, it's basically, but there are things that are easily drawn, and the fun of mathematics doesn't lie in, you know, the fact that it's flawed or that, you know, it lies in finding beauty in ideas. It lies in finding art in places that are not seemingly beautiful. Right? I look here, I look there, doesn't look beautiful, but to me it is. That's what math is all about. It's like anything, it's an art, right? So I'm gonna keep talking about derivatives. There's notation for derivatives. For me, notation means nothing. Okay? Notation is just something you have to memorize. It doesn't mean anything. If I was the professor and you got the notation wrong, and you could prove to me that you got the notation wrong, instead of, you know, actually getting the problem wrong, I wouldn't care. I'll give you back the marks. But I'm not your professor, so you have to know the notation. I'm not gonna obviously write them out on anything because it's available online. Sorry, my toe is itchy. My toe, my toe. But um, mm, so that was awkward. But um, yeah. So you have to kind of look it up yourself. There's Leibniz, and then there's the normal Leibniz DDX. Yeah, there's Leibniz notation. I think that's the most common one. Then just the f of x, f prime x, which is just using an apostrophe between the f and the bracket. F of x, f prime x, f double prime x to denote higher and higher and higher derivatives. One thing though, just because you're going up derivatives does not mean you're changing from one variable to another variable. It just means you're taking the derivative and you're taking the derivative of the derivative, because the derivative of the function, if that is also a function, you can take the derivative again. So that's that. And what else is there? Okay, let's get into derivatives. Derivatives is well, I would imagine the first thing that derivatives came from is physics. Okay, so I want to know. She's probably not in physics, but probably some person was swinging a ball. Probably they saw like one of these people, one of these Olympics in the old days with the Greeks, or something like that. They were swinging a ball, and then once they let go of the ball, the ball travels straight. Like, that's the idea of derivative, really. Derivative is if I seize, looking at its current path, okay, it has a path, I don't know what it is, and I'm cutting everything off at the current place, okay, current place, I'm cutting it off. As it keeps going, I keep seeing more and more, and I'm able to observe more of its trajectory. Okay, I'm able to observe more, and then what happens if suddenly I just let go? What will the path be? Something, the path will keep turning, but that does not make sense. Look at physics. If I do it in the air, it goes straight, except for gravity, which is another force. Imagine then a mental experiment in outer space, in the middle of nowhere, or in a room where there's no gravity, there's not any forces. You stand in the room and you throw a ball. There's no air resistance, nothing. Ball would travel straight. That's the idea of the derivative. And the problem that a lot of people encounter, which is a very simple problem to solve, and actually it leads to an idea that is extremely interesting. The problem that arose was this problem with, I forgot it. I'm so tired. It's a bad day. It's from this problem where so you can't take a slope at a single point. Right? That's the problem, because slope at a single point just doesn't make sense, because the formula for slope requires that you use 2 points. Alright, so you have to do rise over run. You take the difference in y divided by the difference in x. F of y1 minus f of y2 over x1 minus x2. Or if that doesn't make sense, f of x2 minus f of x1 over x2 minus x1. Basically, you have to pick the things to subtract from the same point. If this, you have to choose the initial and the terminating point. If I choose this one, and here, this one is the f of x2, this one is the x2, this one is the f of x1, this one is the x1. You cannot f of x2, x1, right? So then, okay, what happens is they find this stupid way. Well, basically, a lot of people explain it in many different ways. The concept of limits, they explain it in very different ways, and they make it overcomplicated. Basically, limits is, as always, people think that mathematicians are nerds and smart and very gentlemanly. But the real mathematicians, those are the rascals. right? Those are the guys who in kindergarten, they were the guys, cheating on tests. The teacher asked them to do the Sudoku. They went on their computer, they searched up Sudoku solver, inputted the Sudoku, solved it, got perfect marks. Asked the brother to solve it, saying that they're gonna give them candy. Those are the real mathematicians, because they like stuff like that. And they cheat. So the whole idea of the limit in mathematics is basically just a cheating tactic. Okay, I can't, basically means I can't say this. I can't say, oh, I'm dividing by 0. Because that's what it means, right? You take, if it's, if the slope, the 2 points are together, you would have to divide by 0 in order to come up with a slope. So that's what they introduce limits. Now we have limit as things go to infinity. We have limit as things go to 0. Those are the common ones. Okay, because those are the ones where things mess up. For the limit as something goes to 0, it means it just says arbitrarily close to 0. Okay, there's a proof for it. It's called delta epsilon. That's the proof for the limit, definition of a limit. I'm not familiar with it because I skipped that part in my class. But basically, from what I remember myself studying, is the delta epsilon proof means the whole idea is, instead of trying to, whatever, right? If the limit exists, then it only cares about everything except a point. So basically, what happens is you take any any epsilon, small enough, no matter how small. Take any epsilon. You prove it for all epsilon, meaning any size, and you find the delta such that the function is contained within it. No matter how close together, how tight the thing is, you can squash it together so the around this point, it's held within, because that means it's going into this point. That is what it means for a limit. A limit can be, there's several types of limit failures. Alright, let's talk about limit failures. The first limit failure is there's a gap, right? It jumps. That's not a limit, right? The limit doesn't do anything because from the left hand side and the right hand side, they're different. That's the first problem. The second problem is there's a discontinuity, right? It goes to infinity. It goes to infinity. Think of 1 over x or 1 over x squared. Just look at those. 1 over x, f of x equals 1 over x, f of x 1 over x squared. The third type is an oscillating, right? Think of something like 1 over sine x. So, something over 1 over 1 over sine x. Pretty sure. So, yeah. So 1 over sine x. 1 over sine x or 1 over sine of 1. I really need decimals. I can't figure out what this function looks like. I think I'm talking about the one that like goes crazy. Oh, that's sine of 1 over x. Yeah, sine of 1 over x. Yeah, I'm talking about now sine of 1 over x is also a limit failure, because it doesn't, as you at 0, as you get closer to 0, the closer you get, it doesn't divert, it doesn't go towards anything. You know that sine of 1 over x, yeah, because you can't even go with 1 over x, because 1 over 0 is not defined. Because logically it doesn't make sense. Why does 1 over 0 not make sense? Because 1 over 0 is like, I have 1, I have 1. I'm dividing it into 0 pieces. If you have limit 1 divided by close to 0 pieces, then it's almost infinity. That's why you see 1 over x, as x approaches 0, it will go to infinity, a negative infinity. Because, you're kind of blowing it up, because you basically, as you get close to it, it goes, how do I say this? Let's say I have 1, and I'm dividing it by 1/2. That's 2. I'm dividing it by 4. That's 4. Dividing by 8. That's 8. So I just take, instead of doing something complex and arbitrary, let's just do 1 over powers of 2. Well, if you have 1 over power of 2, 1 over 1 over powers of 2. So I'm talking, I don't really want to do this all the time. I think my notation is probably atrocious, but you see that? Yeah, so I don't even know if what I'm writing here is correct, but basically it's, if you take powers of 2 and you do, obviously 1 over a very large power of 2, I should use a power of 10, but I use the power of 2. Well, power of 2 is more simple, so I guess that is elegant, but it's kind of stupid, to be honest. Whatever. So, yeah, powers of 10. So, powers of, powers of, yeah, so if you even powers of 10, I think I'm gonna stick with powers. So basically, you can see how 1 over 1 over 1 over anything that is the same thing as just the number by itself at the bottom. So you arrow the powers of 2, you're just going to get powers of 2 in the numerator and whole numbers. And if you do powers of 10, you're just going to get whole. That's why it's infinity goes to infinity. So now we're going to talk about derivatives finally. Derivatives is not really interesting. So basically, as I said before, now that you have the limit, it's a cheat. It's a cheat code, right? I can't be exactly that, but I can be close, right? So what happens is, I'm close, right? So, I solve the equation, and I'm gonna take 2 points that are very close. And the idea is, if I put them at the same place, that's not gonna work. How far apart is far apart enough? How far apart is it enough? Well, the best would be no matter how far apart, any far apart, it works. As long as it's not 0, as long as there is a far apart. So that comes to the delta epsilon proof. As long as the far apart is greater than 0, as long as there is a far apart, then it's okay. That's the idea, right? And it's amazing. You're like, boom, wow. As long as there is. So every single far apart in the domain, or the range, I can't remember. Range, yeah. No matter how close together it is, right? How close the value of the function is, I can squeeze it close enough that it's held inside. That is the definition of the limit. That is the proof. It's called delta epsilon proof. You take an epsilon greater than 0, and for that epsilon greater than 0, you think about it. Let's say you write, given an epsilon greater than 0, there exists a delta such as f of I messed this up. What is it? So I forgot how to do the epsilon delta proof. I know the theory behind it. The theory is you're trying to trying to use logic to set things up in such a way that you're squishing this rectangle smaller and smaller and smaller, and you're proving through a proof that any rectangle, no matter how big, how small, anything, always works, that the function is contained within this box. And when you get closer and closer to the if it works for everything, which is what any epsilon delta proof does, it proves that no matter how close you get, you are still within this distance from the the the, the point, right? This allows you to have a point somewhere else at that point there. It takes away the syncopated type of structure, syncopated type of syncopated type of function. Yeah, it just really helps to do that, but I forgot how to do that. I think it was there exists an epsilon such that for all delta greater there exists an epsilon greater than 0 such that for all there exists a delta greater than 0 such as for all epsilon greater than 0 L minus epsilon minus L okay, whatever. So there's something called a delta epsilon proof, which I'm totally not getting. Because I haven't studied it. So that's that. But the main idea is what I said. Then we're going to do derivatives. I'm just going to finish this quick. It's you take f of x plus h minus f of x over. So it's this formula that basically puts the 2 points closer and closer and closer together. Puts the limit of the 2 points closer and closer together, and then they do some arithmetic and some things cancel out, and basically you're left with a formula. That's it. That's all derivatives. It's not complicated.